In this video, we're going to run through a few different questions involving this state of stress given with sigma x equals 10 megapascals, sigma y equals 50 megapascals, and tau xy equals minus 10 megapascals. We're going to use Mohr's circle in the first question. So question 2, we're going to go through question 2 through question 5, again with the same state of stress. We're going to use Mohr's circle in all these questions, and the first question is asking us to use it to determine the larger in-plane principal stress. Well, let's get started by drawing Mohr's circle, and the first step to drawing Mohr's circle is calculating out where the center of Mohr's circle might be. So for that, we can say that we have the sigma average, which is going to be the x-coordinate for the center of Mohr's circle, and is the average of the sigma x and sigma y. So it's just going to be 10 megapascals plus 50 megapascals divided by 2, which comes out to be 30 megapascals. We draw the sigma and the theta, sorry, not theta, the tau axis as shown. Tau is positive going downward. This follows the convention in Hibbler's book. And the center of Mohr's circle, as we stated previously, will be at sigma average, comma 0. The vertical component of the center of Mohr's circle is always 0, so it's going to be on the sigma axis. The next step we can follow is to plot a point on Mohr's circle given the state of stress in a particular orientation. So we've been given a stress, sigma x equals 10 megapascals, sigma y equals 50 megapascals, and tau xy equals minus 10 megapascals. We could pick sigma x equals 10 megapascals, comma, tau xy equals minus 10 megapascals, if we like. Or we could pick sigma y equals 50 megapascals, comma, negative tau xy, which would then be 10 megapascals for our point on Mohr's circle. Both of these points would be valid. We're going to go ahead and proceed with using sigma x and tau xy. Sigma x is less than sigma average, so it's going to be left of the center, and we can draw sigma x as so. Tau xy is negative, which means that it's going to be above the sigma axis. And so we can draw a horizontal line representing that distance as we see here. And the point on our circle will be where these two dashed lines intersect. The radius can be thought of as going between the center and any point on Mohr's circle. And so this is a point on Mohr's circle, and so we can say the radius is such. And Mohr's circle can then be drawn very roughly, you can see my beautiful circle, by just rotating that vector r around the center. And we can calculate what that radius is a couple of different ways. One would be to use the transformation equations that we've discussed previously, but since we're doing Mohr's circle and we're embracing this geometric approach, let's go ahead and use geometry. And we're going to harken back to Pythagorean's theorem. What is Pythagorean's theorem? It says, well, if I have an adjacent side and I have an opposite side on a right triangle, I sum and square them, or I square them and then sum them together, that's going to be equal to the hypotenuse, the length of the hypotenuse squared. So what do we have here? Well, r is the hypotenuse, and we have this opposite side, which is tau xy, and we have an adjacent side, which is going to be the sigma average minus sigma x. So we can write out that the radius will be the square root of the sum of these squares as such. So radius is equal to the square root of the sigma x minus the sigma, the sigma average minus the sigma x, quantity squared, plus the opposite, or the tau xy squared, as you see there. And this comes out to be the square root of this quantity 10 megapascals minus 30 megapascals squared plus quantity minus 10 megapascals squared. And the resulting value is 22.4 megapascals. Notice that the tau xy was squared and it was negative, and so it's a positive. And here it doesn't really matter if I do sigma average minus sigma x or sigma x minus sigma average, because when I square that, I'm going to get a positive value as well. Let's go ahead and think about what the state of principal stress looks like by drawing the sigma 1 and the sigma 2, as you see here. So the rightmost point on Mohr's circle is going to be our larger in-plane principal stress, and sigma 2 is going to be the smaller in-plane principal stress. In this question, we're concerned with finding the larger one, so sigma 1 is going to be equal to sigma average plus r. That's this distance plus, actually that's the radius, right, plus the sigma average down here, or sigma average plus the radius. This is also radius on the horizontal. So we have 30 megapascals for a sigma average, and we have 22.4 megapascals for radius, and the resulting answer is 52.4 megapascals. So we have successfully found the principal stress, or the larger principal stress, and the smaller principal stress would be just sigma average minus the radius. So that would get us to being at something like 7.6 megapascals. Let's go on to question number 3. Question number 3 is going to involve determining the angle of rotation required to get to a transformed state with principal stresses. Well, we were just describing the state of principal stresses, so we're going to copy what we did in the previous question, number 2, in this session, and go from there. Now, we want to find the angle of rotation, and we haven't described the angle of rotation yet for getting to sigma x becoming sigma x prime equaling sigma 1, or sigma x becoming sigma x prime and equaling sigma 2. You can also think about if we had drawn the sigma y out on this side, that's 180 degrees. You could think about, okay, how do you rotate that up to get to sigma y prime then being equal to sigma 1? Or how do you rotate it this way so that sigma y prime would be equal to sigma 2? Both would be describing the same state of principal stress, or having them flipped, where sigma x is one of them and sigma y is the other one. Okay, so they're essentially equivalent, but they represent a rotation of 90 degrees on the material element, or rotation of 180 degrees on Mohr's circle. Well, let's draw out the rotation that would take us from sigma x to a sigma x prime. That would give us sigma x prime equal to sigma 1, given the way we've drawn these stresses in this problem. So for this, we can see that this is the angle we want, but how are we going to get there? Well, we know that the angle between, say, this line and this line is 180 degrees. So if we knew the angle in this triangle, we could add it to the 2 theta p and be able to get 180 degrees. So let's go ahead and call that angle in there phi. And there are multiple ways that we can figure out what phi is using sine, cosine, tangent, using these trigonometric functions. What am I talking about? Well, look, we have an opposite length as given as tau xy, or minus tau xy, if we want to think of it in terms of a nice positive number, 10 megapascals. We have this adjacent side, which we have described as being the sigma average minus sigma x. Again, if we want to keep it positive, sigma x minus sigma average is a negative number in this case. And we know the radius. We calculated it previously. That's the hypotenuse. So using Pythagorean's theorem, or sorry, not using Pythagorean's theorem, we already did that. Using a trigonometric function with two of these three sides, we can figure out what phi is. So let's go ahead and do or use sine phi, and that's going to be equal to minus tau xy to give us a nice positive number, and divided by r. Okay, so that's the opposite over the radius. What values do we plug in here? Well, we have 10 megapascals because it's minus tau xy over 22.4 megapascals, which is the radius. And we can write phi is going to be equal to arc sine of 10 over 22.4, canceling out the megapascals here. And that comes out to be 26.5 degrees. Please be careful when calculating these arc sines, arc tangents, arc cosines, just in terms of looking at the answer, and does it make sense to be either in degrees, or does your answer make sense? That's a good thing to always do. But whether your calculator or the way you're calculating it, or your Python is spitting out spitting out radians or angles in degrees. So we said that the angle here, 2 theta p and plus phi, would be 180 degrees. And this angle, the way we've drawn it, is clockwise, and that is opposite of what we consider to be positive with the Mohr circles that we're drawing. So let's just think of it as the magnitude of 2 theta p plus the phi is going to be equal to 180 degrees. So the magnitude of theta p is going to be equal to 180 degrees minus this 26.5 degrees divided by 2. This comes out to be 76.8 degrees. Now, this 76.8 degrees is not this angle 2 theta p. I mean, it's half of it, right? This 76.8 degrees is describing the rotation that the material element would have, while on Mohr circle, it's twice that. It's also describing, as we said previously, this clockwise. If we're going from this radial vector and rotating it to this theta 1 vector, or this radial vector where the sigma x prime would be theta 1, it's going clockwise. And so we can say that this rotation of 2 theta p is clockwise, and that theta p would actually be minus 76.8 degrees. So if we come back to this material element and we say theta p is minus 76.8 degrees, it's not going counterclockwise, it's actually going clockwise, and it would go down, such that this sigma 1 would be spitting out of a square, or a rotated square, that is pointed in this quadrant 4, if you want to think of it that way. Okay. Now, there is also another theta p, or maybe infinite if you start adding 180 degrees to things, and you just go around and round and round and round, or subtract 180 degrees. So here, or I guess if we're adding, it's that way. Okay, anyway, you know what I'm talking about. So this other theta p would essentially just require rotating a smaller amount. The magnitude would be smaller, and take sigma x and get sigma x prime to be equal to theta, or sigma 2, okay, as you see there. So that's just taking this phi, dividing by 2, and it's actually a positive number because it is going to be going counterclockwise. So phi over 2 to get sigma x prime to sigma 2 would mean that phi, or the theta p, or the phi is already 26.5 degrees, but the 2 theta p would be equal to 13.3 degrees. So about half of what you have for phi. Okay. So there are two. Sometimes it depends on how the question's worded. If we want the magnitude to be less than 45 degrees, well then uh, this counterclockwise 13.3 degrees would satisfy that. Obviously, this is greater than 45 degrees. But both are essentially describing principal stresses, or a state of principal stress where you would have a sigma x prime equal to sigma 1, and then sigma y prime equal to sigma 2, or you would have a sigma x prime equal to sigma 2 and a sigma y prime equal to sigma 1. That is question 3. Now, let's go to question number 4. For question number 4, we're going to be looking at the maximum in-plane shear stress. And in this question, we have the same state of stress we started with previously. We have sigma x equals 10 megapascals, sigma y equals 50 megapascals, and tau xy equals minus 10 megapascals. So let's go ahead and just copy and paste what we've done previously and bring it into this sheet. I understand that you might not be so fortunate to have these three values of stress being the same for every problem. Nonetheless, you'd go through the same process that we've described previously and get to this point. So now we're interested in attempting to figure out what the maximum in-plane shear stress would be. Well, where does that happen? It's going to happen where tau is a maximum. And so tau is going to be a maximum here at this location. So at the bottom of Mohr's circle and at the top of Mohr's circle, we have tau max and we have tau min. They are the same magnitude. This one's negative, this one's positive. And in shear stress, often it doesn't really matter, if it's positive or negative, if it's like the angle of twist. And so it's not the same as describing a positive a tensile stress and a negative compressive stress. But let's just say that tau max, we'll say it's positive, and that can be equal to the radius of this Mohr circle. So tau max is just going to be equal to r, and r was 22.4 megapascals. So question number 4 is pretty fast if you've done all the prior work. Question number 5. Question number 5, as you might guess, is to determine the angle of rotation that's required to get to a transformed state with maximum in-plane shear stress. And here, I'm a little more specific and say that magnitude, at least on the slide, magnitude should be less than 45 degrees. So let's go ahead and paste in all the work that we've done previously, including this tau max value on the previous slide. And now let's think about the angle of rotation that's necessary to go from this sigma x comma tau xy location to either the top or the bottom. Well, it says that we want the angle of rotation to be less than 45 degrees. So going up to the top is our option. If we go around here, right, we know that this is over 90 degrees on Mohr's circle, which is going to correspond to an angle of rotation for the element greater than 45 degrees. So let's go ahead and think about this rotation that's necessary. Once again, we're going clockwise, which is going to be a negative rotation of the material element, or negative rotation on Mohr's circle. And we'll say that this is 2 theta s to go from this radial vector with sigma x, tau xy here, to a sigma x prime where we have tau x prime y prime equal to the tau min. What is the angle of rotation? Well, it's going to be dependent on phi. We've calculated phi previously, so we know that phi plus the magnitude of 2 theta s is got to be equal to 90 degrees. So we can say phi plus magnitude of 2 theta s is equal to 90 degrees. Before we were saying it was equal to 180 degrees and going over here. We can solve for theta s, and it is the 90 degrees minus the phi, all divided by 2. And this is going to be equal to 31.8 degrees. In case I wasn't clear that the theta s, the s, that means shear, or state of in-plane shear stress, versus when we had the theta p's previously, those were standing for the angle associated with maximum in-plane principal stresses. So we said this previously, the counterclockwise rotation, the clockwise rotation is going to be negative, and that means that theta s will be equal to minus 31.8. Okay, so in this video, we have calculated or both principal stresses really, okay, from a given initial state of stress. We've calculated the angle required to get to a state of principal stresses. We've calculated the maximum in-plane shear stress, and we've also calculated the angle of rotation necessary to get to that state of maximum in-plane shear stress. I hope you find this video helpful. Thank you.